Alright, what we're going to be looking at in this session is what I would call two curly arrow mechanisms. And what I want to do to begin with is talk about the use of curly arrows in organic chemistry, because there are some conventions that you need to follow. A curly arrow, first of all, has to be curly. And it has to have a double head. There are also single-headed curly arrows, but they mean something different. A curly arrow, like this, is used to represent the movement of a pair of electrons. That is what they're there for, okay? And when you use this notation, you are showing the movement of a pair of electrons. This symbol shows the movement of an unpaired electron. So, the only place in the syllabus that this is likely to come up is there, to show homolytic fission, okay? Which we discussed in the previous session. Here, one electron goes each way. But from here on in, you're going to be drawing double-headed curly arrows. You cannot draw straight arrows and expect them to have the same meaning, because they don't. Okay? Right. There are two rules of organic chemistry. Okay? And if you follow these two rules, you will be able to work out any mechanism in an exam condition. I don't want you to learn the mechanisms by route. I don't want you to remember, I have this structure, this is what happens, pretty picture, the end. I want you to understand what is going on at each stage. And I want you to realise not just what happens, but why it happens. You happy with that?
Yeah, man.
Right. There are two rules. One, identify the positive and negative bits. Two, the negative goes to the positive. That's it. Okay? Rule 1, identify the positive and negative bits. Rule 2, the negative bit goes to the positive bit. It is never the other way round. It is always negative bit attacking a positive bit. Okay? Right. So, let's have a look at these notes here. And these are taken from chemguide.co.uk. On the right-hand side here, we have an example, which we're going to be looking at later, of a mechanism. And this is a mechanism of electrophilic addition. I said two rules, didn't I? Identify the positive and negative bits. Secondly, negative goes to the positive. HBr. Let's just draw this out. Which of these two elements is more electronegative? Bromine. If the bromine is more electronegative, what does that mean? Definition of electronegativity is the ability of an atom to draw electron density to itself from a covalent bond. Therefore, this pair of electrons here gets more attracted to the bromine, yes? So the bromine becomes slightly negative. Are you happy with that? You happy with this symbol here, the delta? Just means a little. Be honest, anybody not happy with that symbol? Okay? This is delta negative. If that's delta negative, what does that mean about the other end? There we go. Rule 1. Identify the positive and negative bits. Rule 2. The negative bits go to the positive bit. We don't, by convention, put a delta minus on the bond, double bond here. But are you happy? That represents 4 electrons. That represents a whole area of electronegativity, of negativeness. And what can happen is these electrons here can become attracted to that positive there. Make sense? Right. Starting at the negative, curling round, I've got my first curly arrow of the morning. Now, a lot of time gets spent discussing curly arrows, how to draw them, when to draw them, why to draw them, and so on. Start with where the electrons are, which in this case is the double bond. You happy with that? Curl it round and finish with where they are going to. Now, you see different textbooks and different things. Okay? I am teaching what I was taught at university. And what I was taught at university would get the marks on any exam board mark scheme. These electrons form a bond between the carbon and the hydrogen. Okay? They were between that carbon and that carbon. Happy with that? They're going to the space between this carbon and that hydrogen. You got that? In doing so, they end up in the middle, don't they? I don't draw, though you will see it in some textbooks, the electrons going to the hydrogen, because they don't go to the hydrogen. They go to the space between the carbon and the hydrogen. Does that make sense? Now, if this hydrogen has suddenly got electrons from there, does it need these electrons? And bromine's pulling them, right? Because we know, because bromine's electronegative, yes? Or more electronegative. Therefore, those electrons can curl round and they do go to the bromine. The bromine nicks the electrons. Does that make sense? So, from the top, the electrons in the double bond, okay, are able to come out of the double bond and form a covalent bond between the carbon and the hydrogen. Yes? At the same time, this hydrogen no longer needs these electrons from the bromine, and the bromine goes, give me the electrons, I want all the pies, and it takes them. Okay? You happy with that? Right. And what we end up, therefore, is with this situation. What's the problem? What have I missed out? And there is a problem.
That carbon only has 3 bonds.
This carbon only has 3 bonds. Well, it was in a nice, happy little, state. It had got 4 pairs of shared electrons, 4 covalent bonds. It's a happy chappy, and so on. And along comes Mr. Meanie HBr here, and it loses 2 electrons. If it's one of which was its, one of which came from there, but it's lost a pair of shared, but it's lost one of its electrons. If it's lost one of electrons, what's going to have happened to it? Louder? It's not going to be delta positive, it's going to be actually positive. What's the difference? Good question. Delta positive means a little, slightly. Okay? This ends slightly negative, that ends slightly positive. This has now got a full-blown positive charge on it. Okay? It's lost an entire electron. Okay? Now, 2 rules. Identify the positive and negative bit. Second rule, negative bit goes to the positive bit. Yes? What's going to happen? Bromine's got the electrons.
So they move to the...
Yep. And what you get, it's getting quite complicated there. Is it okay on the camera? Can you see it okay?
Yeah. I'll zoom in on it.
You'll zoom in on it. The bromine's electrons can now form a bond between that carbon and that bromine. The carbon's positive, the bromine's negative. Second rule, negative goes to the positive. Yes? In go the electrons, and a bond's formed, and you get that molecule, bromoethane. You happy with that?
Yeah.
That is a curly arrow mechanism. That particular one, I'm going to tell you a couple more things about that, and then we're going to go through the PowerPoint I've got that's associated with this, and we're going to do it all from the top. This molecule here, what does it like about this molecule? The HBr, what does it like about this molecule? What does it want from that molecule? Electrons. This molecule here is an electrophile. It wants electrons. It likes electrons. It's an electrophile.
Wait, what's an electrophile?
Nice and quiet, please. The HBr is an electrophile because it's attracted to the electrons in the alkene. The HBr has been added, in this case, to ethene. This is the mechanism of electrophilic addition, where something that is slightly positive has been added to the double bond. This is electrophilic addition. Are you happy with that? Right. To recap, curly arrows start at the negative bit and go to where the electrons end up. So in this stage they end up between the carbon and the hydrogen. This one here, they go to the bromine. So what you end up with is a covalent bond formed there, a carbocation or a positive ion there, and a Br minus there with its lone pair of electrons. The lone pair of electrons can then go round into there, and you end up with that. HBr is an electrophile. This is electrophilic addition. Got it? Yeah. Okay. Pause for a minute, please.
We're on.
Okay. I've just had the question, what sort of exam question could we get about this? And the answer is, you are expected to be able to draw something like this. Okay? This would typically be a 3-mark question. Okay? And you would be expected to produce something like that. You're going to need to practice this, because these are all going to come up. I'm absolutely certain about the fact that every mechanism on the syllabus is going to come up. Okay? Right. What we're going to look at now, we've got about 15 minutes, is we're going to look at the chemistry of the haloalkanes. So, you all know covalent bonds, we've talked about that. You can all balance equations. You can also all write out structures for hydrocarbons. We've talked about the different types of bond fission and chemical properties of alkanes, alkenes and alcohols. Okay? We'll cover those this morning. Right. We're going to be looking at halogenoalkanes. We're not really going to be looking at haloalrenes. To begin with, halogenoalkanes fall into 3 categories: primary, secondary, and tertiary. Very simply, if your chlorine is on a carbon, and that carbon is attached to one other carbon, it's primary. If the carbon that the chlorine is attached to is attached to 2 other carbons, it's secondary. And if the chlorine is attached to a carbon with 3 other carbons, it's tertiary. Okay? Primary, secondary, and tertiary haloalkanes. All with me so far? Fab. Naming, you should now be happy with, so I'm not going to spend too much time on that. This is 1-chlorobutane, that is 2-chlorobutane. This is 2-chloro-2-methyl-propane. Why? Because you've got 3 carbons all in a row. You've got a methyl group, you've got a chloro group. You are expected from module 1 to be able to name a compound like that. Okay? This, however, is 1-chloro-2-methyl-propane. You should know that greater branching equals lower intermolecular forces. Okay, and it's straight chain alkanes have got higher boiling points because they have greater van der Waals forces. Just pause it for a second, please. Right. If you have greater branching, it means the chains can't line up as smoothly. You get weaker van der Waals forces, and hence you get lower boiling points. Okay? And that you should know already. We're now going to talk about nucleophilic substitution. If electrophilic addition is where you have an electrophile and it gets added on, nucleophilic substitution is where you have a nucleophile and it gets swapped. A nucleophile, put simply, likes nuclei. Nuclei are positive, nucleophiles are negative or have an available lone pair. Okay? They all have available lone pairs. Some are negative, some aren't. So, let's talk about a carbon attached to a chlorine. The chlorine is more electronegative than the carbon. You happy with that? Which means this end becomes slightly negative. You happy with that? If that end becomes slightly negative, that end becomes slightly positive. And if that end's slightly positive, it means it's open to an attack by a nucleophile.
Is that your innuendo?
No.
Innuendo.
These four are all nucleophiles. They are not all negative, but they all have a lone pair. So here's OH minus, it's negative, it's got a lone pair. CN minus, it's negative, it's got a lone pair. NH3, it's not negative, but it does have a lone pair. And H2O, or water, it's not negative, but it does have a lone pair. These lone pairs make these guys nucleophiles. And these carbons that are slightly positive are open to nucleophilic attack. Right. Curly arrow mechanism. Very simply, a nucleophile attacks the positive, slightly positive carbon. You with me? I said there were two rules. Identify the positive and negative goes to the positive, yes?
Yep.
Positive, negative, and with water or ammonia the lone pair is still slightly negative. Lone pair attacks the carbon. Negative to positive. At which point the chlorine can go, finally, I can eat all the pies. Nix the electrons. The nucleophile has now bonded to the carbon and the chlorine leaves. This is nucleophilic substitution. In terms of which you classify as a nucleophile and an electrophile and so on, you have your organic compound, and then whatever attacks the organic compound, you classify it as either a nucleophile or an electrophile. So there's my organic compound. This is a lone pair attacking, therefore that makes it a nucleophile. Does that make sense? Nucleophile attacks, chlorine leaves. One thing goes in, one thing comes out, substitution. Nucleophilic substitution. Are we all clear about that? So, here are a bunch of points. I think they're pretty self-explanatory. Nucleophile is a lone pair, said that. Carbon-halogen bonds polar, said that. Curly arrow, said that, said that. Carbon is restricted to 8 electrons, okay? If we've got something else coming in, something else has got to leave. You can't have a place where it's got 5 electrons, 5 pairs of electrons. So as one comes in, one goes out. The polar carbon-halogen bond breaks heterolytically, unevenly. So here, both electrons are going to the carbon, which is what that point covers. Sorry, the chlorine, that point covers that. And that I've covered. Are you happy with that? This is the mechanism of nucleophilic substitution. Then we have probably the most amazing piece of computer graphics you've ever seen. In comes the nucleophile.
That is trippy.
Out goes the chlorine. You happy with that? Okay, watch it again. All right, one more time. In comes the nucleophile.
Who needs TV when you've got this?
Yeah, who needs TV? I mean, that's just so much better than TV.
It's actually quite a turn on.
Okay. You should be aware that the rates of reaction depend on the type of halogen that you've got. C to I has got the weakest bonds, C to F has got the strongest bonds. Does it stand to reason? The stronger the bond, the harder it is to break and the slower the reaction occurs?
Yeah.
Good. The stronger the bond, the harder it is to break and the slower the reaction occurs. Therefore, if my halogen is iodine, the reaction occurs faster than if my halogen is fluorine. Water will do this, okay? And we'll come back to these precipitate colours later. We're not going to worry about those now. If you have an OH, out goes the chlorine. You start off with a haloalkane. What type of molecule is that? Alcohol. Haloalkane can be turned into an alcohol by the reaction with OH minus. Oh, I think we've got another little animated mechanism here.
Ooh.
In comes a pair of electrons. Out go the other pair of electrons. And we've got an alcohol. And a Cl minus. Exactly the same thing happens if you use potassium cyanide. Okay? Here comes the Cn minus. Notice the lone pair is on the carbon and the minus is on the carbon. Cn minus is the carbon that's negative. The carbon pair of electrons attacks there, chlorine leaves, and you end up with this molecule here. This is called propan-nitrile. Okay? 3 carbons in a row. We started off with chloroethane and we've made propan-nitrile. All good? We're not going to worry about that now. So here we have another fantastic mechanism. Here it comes.
Revolutionary. New century special effects in.
Oh, absolutely.
Woo.
Ammonia. Exactly the same thing happens. Or does it? In comes the ammonia, out goes the chlorine, but look at that.
It's positive.
It's positive.
Dun, dun, dun.
There is something else that occurs after this one. But at this point, actually, I'm going to draw you a mechanism. Right, there's my delta positive. No, delta negative. There's my delta positive. There's my NH3. There's the lone. You all good? Can you all see that?
Yeah.
In goes that, out goes that, and you end up with that. Happy with that? Just going to cross those out, and I'm going to put on the H's instead. You with me so far? What can then happen is another ammonia comes along. Forms a bond there, and releases those back to the nitrogen. Does that make sense?
Yes.
And then this, stay where you are. You get that? Happy with that?
Yeah.
If you can please just copy down this mechanism, the right-hand side of this slide, and pause for a second. We looked at how OH can act as a nucleophile to a haloalkane. And we looked at how the Br can be replaced along the lines of this. In comes the OH, it attacks that positive carbon, the bromine leaves, and you get ethanol where before you had bromoethane. We happy with that? Remember doing that? Remember writing the mechanism for it and so on? It turns out OH can do something else as well. Beforehand, this is a critical distinction. Pause please. Right. Beforehand, OH was acting as a nucleophile, but it can also act as a base. And if it acts as a base, it has a different mechanism. What it does here is it acts as a base and it takes a hydrogen. So, in comes the lone pair, attaches to that hydrogen. The electrons from the hydrogen go to the carbon-carbon there, and the bromine leaves. And what you get is an alkene. It can act as a nucleophile and do nucleophilic substitution or elimination. And it turns out that it's all about the conditions in which you have the OH. If you have, and I've got the back of the page, aqueous, if it's in water, the OH behaves as a nucleophile, you get substitution and you get an alcohol. You happy with that? If it's dissolved in an alcohol, it behaves as a base and you get an elimination reaction and you get an alkene. Okay? And I want you to add to this alcohol here, hot. Okay? Hot ethanolic sodium hydroxide and you get an elimination reaction. Okay? If you have aqueous hydroxide, you get a substitution reaction. If you have aqueous hydroxide, you get a substitution reaction. If you have hot ethanolic hydroxide, you get an elimination reaction. And I think that's all I really wanted to talk about. You should be aware, of course, that hydrogen can be removed from either side. So if you remove that hydrogen, you get but1e. If you remove that hydrogen, you get but2e. Now, a lot of pupils get this mechanism horribly wrong. And what they try to do is they try to remove that hydrogen. If you remove that hydrogen and that chlorine, you get some horrible double carbocation thing that can't exist for very long. You've got to nick the chlorine and a neighbouring hydrogen. Be that one, that one, that one, that one, or that one. Doesn't matter. Okay? And to do that, you need hot ethanolic sodium hydroxide. Okay. Haloalkanes, we've talked about polymers, and that's all I really want to say about haloalkanes. Quick reminder about the ozone layer though. Okay? CFCs get broken up, produce chlorine radicals, and the chlorine radicals then break up ozone. Back one. Here's your reaction for that. O3 plus Cl dot goes to ClO dot plus O2. That then reacts with O3. We did. We changed it. We went ClO dot plus O3 goes to 2O2 plus Cl dot. So just change it again here. ClO dot plus O3 goes to 2O2 plus Cl dot. Okay, so the chlorine radical is regenerated, okay, and goes on to destroy more ozone. Okay. Pause there.